को तुम्ही से चुरा लूंगा मैं, मुझको इबादत दो का। Welcome back, everyone. In this week of reinforcement learning, we'll be solving from few problems from week 3 here, and we'll be starting in few minutes now. Okay, so let's start. Only 3 people I see. Okay, maybe cricket match thing. Otherwise, yeah, used to see around 8 people here. Okay. Okay. So topic is the week 3. So just let me write this down. Okay, so starting off with the first problem. So the baseline in the reinforce algorithm is there. Reinforce update should not depend on which of the following without voiding any of the steps in the proof of the reinforce. Okay, so this is the question. Uh, okay, so so how do we approach this problem? So the thing is to go back to the theory that we have here. Okay, so for that, So so the problem that we had was that uh, you have so you're evaluating a policy, and that eta theta that we have got. Okay, so let me write it down. So evaluation of the policy, so we have eta theta here. Okay, and this we have represented as expected payoff. Okay, so expectation of payoff, and payoff is RT. Okay, so this is the situation we had. This is general problem. Actually, we are not going to the reinforce right now. Okay, so but let me explain from the start. So now this becomes summation over all the actions. Okay, and q star a optimal optimal true expectation. Okay, for a arm a. Okay, and the probability pi of taking action a given some parameter theta. Okay, okay, so this is our expected payoff. Okay, and this is, so we have to move theta such a way that we get to maximize this eta theta. Okay, so what we're doing, we are moving the direction of eta theta using a gradient ascent algorithm. So these I have seen in the lectures. Okay, and this is learning rate, as you would know. Okay, and so this is the situation we have, but the problem is that we cannot have a deterministic formulation of this eta theta and use this for batch gradient descent, because we do not know eta theta, because one component of the eta theta, that is q star a, is our actually real problem. We cannot solve this one. Okay, this is actually the what we want, actually the expected true expected reward for each arm. Okay, so this is the true expected reward for each arm that we need to calculate. So this cannot be solved in this algorithm. Okay, so batch formulation of this algorithm is not possible practically. Okay, so this is where we need some stochastic algorithms. Okay, and so stochastic gradient ascent we come up with, and so the formulation I will again write it down. So just to give you something, so this is what we need to find, but we cannot do it because of the q star a. We do not know that, so we need a stochastic formulation, some estimation theory. Okay, so what we are doing here is that our this is the one. Okay, so I'm not writing it again. So this is there, and we write it as summation. This is one way to solve it. Okay, this is not the reinforced algorithm. Okay, this is a batch algorithm. Okay, we are taking n batches here actually, and n represents the number of states, actually, you can say. So so summation over a, and this is q star a, and del theta pi. So this is what we had actually, a comma theta. Okay, so we need to find the gradient of this. Okay, so what we do is divide by pi a theta and multiply by that as well. Okay, so multiply the same, so it remains same, and but we can, what we can write is that this is the expectation of this quantity with respect to this pi a theta, right? And what this becomes is summation n equals to 1 to capital N for n batches of this steps. Okay, what we are doing is that this becomes expected payoff, expected reward. okay. Rn del theta. So this is what we'll get, okay. But we do not need this one. Just to recap, actually I'm doing it. Okay. So we are taking n batches actually here. So that is how we are getting this one. So after this once calculation, what we'll do, we'll go back to here and update theta, then again take n more, calculate this again, then update theta again. It continues up till convergence. Okay. Now what we have here is that uh, so the our question comes here actually, that this reinforced algorithm. So this reinforced algorithm is actually right now coming. So it is a one step at a time algorithm. So very high stochasticity and variance here in this algorithm, and that is why it is slow to converge. Okay, because only we are updating at every step actually. Okay, at every sample. Okay. So the formulation is like this. That what you have here is that, so we write here as q, okay, qn at nth step, okay, is equals to alpha n rn and del pi, that an comma theta n, okay, and pi an comma theta n. So I write it down now, so same above it as well. Okay. So this is the, and this update rule is this, very simple actually. This just add this del qn for distributions. Okay, so pi is a probability distribution, as you can understand. So density function actually, and for distributions which are like normal distribution which have exponential, so taking the derivative can be difficult, so we have another log form for this. Okay, and this is del qn. So another log form is this one, qn rn, no, not q, alpha actually, alpha n rn del by del theta ln pi an comma theta n. Okay. So this is our formulation. So this algorithm is called the uh, reinforced algorithm, but another more improved version, it's like which reduces the stochasticity and leading to a quicker convergence, is more stable convergence as well, in which you are using a baseline. Okay, so the definition of the baseline I will explain. So in place of rn, there is rn minus pn here. Okay, and the rest remains the same. Okay, so the pn is called the baseline here, and so the Pn is usually defined as the sum average of, I mean, arithmetic mean of all the reward up to this that step. Okay, so Pn at step 1, P1 will be Rn. Okay, then after that it will be R1 plus R2 by 2, then R1 plus R2 plus R3 by 3. Okay, like that. So so this is the definition of the Pn. Okay, usually it is, it somehow means this is what is used. Okay, but the overall idea is that Pn will somehow use the idea of all the Rn up to that, up to nth step. Okay, some sort of averaging it will do. Okay, if not the simple averaging. Okay, so our problem, we come to our problem. Okay, so the baseline in the reinforced update should not depend on which of the following. Okay, so the idea is that it is the average of the R1 to Rn. Okay, but it is not, it does not take account the action. Okay, it does not depend on the actions. The answer is this one. Simple, coming from the theory. Okay, any doubt here? Any doubt? You can see the slides.
No.
Clear, right?
Yeah, clear.
Okay. Okay. Uh, so 6. I'm saying somehow. So 2 in me and 4. Acha. Okay. Okay. So first question done. Next question we're going to. Uh, so which of the following is true about RL, about the RL problem? So our main aim is to maximize the cumulative reward. So that is correct. Okay. In a full RL setting, what we are doing is that we are not going to maximize the reward at one state. Okay, at multiple states the reward means the sum of the reward has to be maximized. Okay, so that is also there. So it is called return actually. Okay, so cumulative reward is called return. Okay, that has to be maximized. Okay, some, so that is our that is actually with the extension from immediate RL to full RL problem. So in this week we have extended from immediate RL to full RL. So the if it is called RL problem, so the importance as step is that we are extending from immediate RL to full RL, and the most important step is that you are taking a cumulative reward, not a single reward of any step. Okay. uh, so agent perform always in a deterministic function. So that's not correct at all. Okay, it can be probabilistic. Okay, and we assume that the agent determines the next state based on the current states and action. It may not be. It may not decide on the current state and action. Okay, it is impossible to have a zero reward. Zero reward can be there, but the full algorithm should not have zero reward. Okay, so first option is our answer. Any doubt is in this? I'll also write the equation of the returns after this. You're clear on this problem now? Okay, clear.
Yes, sir.
Okay.
Yes,
Uh,
sir.
okay. So proceeding. So I'll just write the equations the Rn, means not Rn, return, which may be useful later in the subsequent question, and that is why I write this one full, because it may be useful later as well. So coming on. So this return gt, it is denoted by gt. It is the r t plus 1 plus r t plus 2 till r t. Okay, and t depends denotes the end time, which is non-deterministic. Actually it can end at any time. The value of the t is not known, capital T. So summing of all the reward scores here, and there can be various rules of summing up. This is a simple sum. Okay, and another is the sum weighted sum. So the importance of the weighted sum is that you are giving a delayed reward. Okay, what means to say is that okay, like dot 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 dot. So gamma to the power n it goes to. Okay, uh, so so the thing is that if gamma is usually not usually like almost always. Okay, or always only gamma is always between 0 and 1. And so what it denotes is that you can see that the reward that we get at subsequent steps reduces because the gamma's power increases, and when the any value is between 0 and 1, if the power increases, then it becomes less and lesser. Okay, so what it means is that the earlier you get it, the more reward you get. Okay, means so that is like more desirable. Okay, like you end up into your solution more quickly. Okay, so that is desirable, of course. You do not want to spend steps into learning it, more steps. So that is how uh, so this is formulated. Okay, and another is the average reward function is there, which is just the average of these. Okay, the sum, that one is there. You take the sum average of that. Okay, that is it. Okay, so we move on to the next problem now. I don't think we have any doubt in this. Any doubt?
No, nothing, sir.
Okay, so let's proceed. So this is that reinforced algorithm only. So we have to use what we have written here. So this is the one we're using. This pn is not required this time. Okay, and because it's exponential function, means like normal distribution, which is exponential function, we're going to use this formulation for del n. Okay, so let's take this forward. uh, so not able to see the option. Enter a new slide here, then paste. Okay. So this is our thing, and this is our question. We need to find the para means with the, so there are so as you can see there are this is theta. Okay, so theta can be n dimensional. So here theta in our case is two dimensional, mu and sigma. Okay, so we need to find the algorithm for both the mu and sigma. Okay, and so okay, so the algorithm formulation is going to be like this. So mu something, and the similar formulation for sigma as well, plus this del q terms, which are we going to calculate. Okay, so in this case you can see that alpha are not changing with time, or is it? Achha. First let me write down the distribution that we are encountering here. So it is a normal distribution. Okay, and so we'll write the general PDF of the normal distribution. So this is a probability distribution for action A, mu and sigma, and the probability distribution is 1 upon under root 2 pi sigma square. Sigma square of sigma is there, e to the power minus a which you have to write like at minus mu square by 2 sigma square. Okay, so just let's check the PDF if we have not done any mistake. the correct formulation. You got this one, okay? And okay, and what more do we have here is, so these are also time dependent. So this is mu t and this is sigma t, okay, like that. This is also sigma t. And now insert another slide. So this is our formula that we need, okay? Alpha are not dependent on time here, as given in the options. You can see Rn is there, so these are common term in both for mu and as well as sigma, okay? So let's proceed. So first we are taking derivative with respect to, first we are taking logarithm here, okay? And okay, and so as you can understand, when we are taking logarithm, okay, so let me write as well. So when I'm taking logarithm here, the ln 2 pi, and what we're getting is minus half, right? Okay, and plus uh, so this is what we're getting, okay? And so this is the good part actually. As soon as we take not sigma, this becomes at minus mu t square by 2 sigma t square, okay? Now when you are taking derivative with respect to mu t, so what happens is that you can understand these two terms are useless, okay? And so we're taking partial derivative, okay? And so what this becomes, the 2 will come ahead and 2 cancel, okay? And so this becomes mu t minus at, okay? Now so when you're taking derivative, you have to use chain rule, and this will become actually plus, okay? Acha, so okay, but keep it accurate for now. So when you're taking derivative, this minus will go away because we can't get another minus from here, okay? So this is at minus mu t by sigma t square, okay? This is what you're getting, okay? At minus mu t by sigma t square, okay? Right. Now next, so this is the term for the mu part, okay? So you can check the options right now and points on answer. So I think this is the one I think we are getting for mu. Okay, so this fourth option is correct, okay? So fourth option, there are two options, 2 and 3, B and C here, okay? B and C, there are two options that match, okay, with respect to mu. Now we'll need to focus on the sigma part, okay? So what we're getting when taking derivative with respect to sigma t is, so once sigma t will come down first, and then and minus will be here, so minus 1, okay? Minus 1 by sigma t, plus what we're getting is that upper portion will be there, okay? And minus 2 will come forward, so this will become 2 cancel, okay? And this becomes sigma t cube, and the upper portion remains the same, something like this, okay? So this is what we are getting, okay? Now checking the options, what we get here, so I think this is the one which satisfied, okay? So 2 is the answer. So I think this is the answer. Okay. Any doubt? Clear? Everybody done with this one? A lot of calculation in a small slide. Clear? Any doubt?
Clear, sir.
Clear, no? So moving on to the next problem. So 3 problems here. Actually, very easy problem. Stochastic gradient descent or ascent. So is expected to occur in the right direction. Right direction it may not occur as well, because so that is what it represents, that stochasticity. एक मिनट. क्वेश्चन रिपीट हो गया. So it may not occur in the right direction, okay, because the fact is that that when you are taking few at a time, it may not point towards the right direction. Okay, so the answer is false. Okay, in a full RL environment, after performing each action, we get an immediate non-zero reward. So not necessarily. Okay, the answer is no, because that return formulation, you can see that after many steps, means after summing all the steps, we're getting a reward. Okay, so not immediately. Okay, in full RL problem, which of the following is not determined by the environment? uh, so reward is not determined by environment. Reward is determined by the user. Okay, so answer is reward here. Okay, any doubt?
No, sir.
Okay, so let's proceed. Now this is the question. Another reinforced question in which we have to update the so there are two parameters here as well, you can see w1 and w2. So like mu and sigma was there, so w1 and w2 is there, and we need to update the parameters here. So this is the problem. So we proceed similarly. Okay, so there are two action states here, and so these are the, so we first go to the place we have written the reinforced equation. So these are the three equations. So one more thing that we need to use here is that so you can see a binary situation with two states actually. So we may need to use the formulation steps of the binary situation. Okay, so I'm going to write it down for both the states. Okay. uh, or what we can do here. Hmm. So, how we are going to do this one is understanding the few things that uh, you can see that we have a linear bandits case. So that is the LRP situation. Uh, so just to formulate some more here, another slide here. Okay. So situation is like this, that if a binary bandits problem, so in which RT can take two values 0 and 1. So if RT is equals to 1, then what you have here is that pi t plus 1 at equals to pi t at plus alpha 1 minus pi t at. So this is the update rule. Okay, so for pi t plus 1 for at, we are doing this. Okay, pi t at plus alpha times 1 minus pi t at. So this is the update rule. What does it mean is that, so previous estimate that we've got this. Okay, so what we are doing, that we are so this is a probability, right? So if you're subtracting 1 minus, okay, so what does it mean, that what is left out, maybe the error. Okay, so alpha times that, okay, we get the new one. Okay, so this is the one. Okay, another is that for under the same RT is equals to 1 pi t plus 1 and a star a dash. Okay, this is equals to pi t a dash 1 minus alpha. Okay, this a dash, what does it represent? A dash is not equals to at. Okay, for so for a given action. Okay, so at is corresponding to RT. Okay, so if it is RT equals to 1, it is, if it's correspond to RT equals to 1, then this is the update rule. Okay, if it does not, then for the another case, so means for so as you can see in our problem, what we have is A2 and A1. So say this is for A2. Okay, and this is A1. So A1 is like this update. Okay, so this is the thing. Okay, another is that we also need to write about the RT equals to 0 situation. Okay, so it is similar, actually, just taking a parameter beta here instead of alpha. So yeah, okay, write it down. So pi t plus 1 at equals to pi t at 1 minus beta. So as you can see, it is the opposite case. Okay, this one's very similar to that. Okay, just we are just using another parameter beta here. Okay, and pi t plus 1 a dash pi t a dash plus beta, just same, using beta instead of alpha, pi t a dash, and this is done. Okay, so now the thing is that what you're given is that we're having a linear bandits case. Okay, so what does it mean is that you're having alpha equals to beta, so these are two state a1 and a2 there. So and this pi definition is this. Okay, and okay, so the thing is that so if these are equal, okay, so what we get here is that it is this. Okay, so for our situation, uh, we can directly use this one. So pi t plus 1 at, so instead of at, okay, at, let's write, so this is 2. Okay, at for 2 2 1 means a2 wala case. Okay, and so and this is pi t at2, and 1 minus that. Okay, and for this one what we have, pi t plus 1 at1, this corresponds to pi t, this at1, and what we have is 1 minus alpha. so so this is our formulation first of all. Next we need this reinforced algorithm. Okay, and need to use this. Okay, okay. So from the reinforced algorithm part, this is the one, right? No, this is the one. Okay, yeah. So for every parameter we're doing it. So here the two parameters are w1 and w2. Okay, so writing the solution here. Okay, so the formulation is like w2, so w2 and similarly for w1 as well. Okay, so what we do here is that we need to take derivative. Okay, that with respect to w1 first. Okay, and how you're going to take it is that derivative with respect to w1 first. Okay, and so our this is here, so let's keep it here. And so what we need to do is that this alpha is there, okay, alpha and Rn is there, so it will be there in both the cases, okay. Okay, and now to take derivative with respect to w1 and w2, so first let's take w1, okay, and for that what we are doing is that this an theta n is there, okay, for two states. Okay, so what we need to do is this pi a2 is there, okay, pi a2s, a2 given s, and pi a2 given s is there, and what we need to do here is plus alpha times 1 minus two different actually to handle this one. Okay, so let's check this problem later actually. Do the other problems here. Okay, and so this is question number 3 here. Here another reinforced problem, okay, in which you have that so if the following is possible expression is for a possible update made when using reinforced for a following policy. So this is a policy given pi a1 theta, okay, and this is equals to sine square theta, okay. So this is what we are updating with. So the a r minus b here, b is the that base one, base r, okay, and after that what we do is take the derivative here, okay, take the derivative, so it's not here, so it is here actually, and take the derivative with respect to theta, okay, of ln of that, we can take ln here, or okay, let's see what we can take. So if we take ln here, so this is 2 ln sine theta, and now taking derivative with respect to theta, what we get is that sin theta comes to below, and this becomes cos theta. Okay, something like this. Okay, 2 will be there somehow. We're getting a cot theta here. So this is there. Okay, another one we are getting here. So idea is something like this. Okay, that so one is sine square theta, and so you can understand the probabilities are complementary. So for like not write it down here, write it down here. Okay, for a1 this is sine square theta. Someone saying something? Right. So for a1 it is sine square theta, and for a2 you can see that it has to be complementary, right? 1 minus sine square theta, 1 minus sine square theta cos square theta. Okay, so for a1, hello, Jocelyn, any issues?
Sorry, sir, I did not notice it.
Okay, so for a1 this is what we have got. Okay, for a2 this is the one. Okay, or am I correct? Yes. So as you can see, for a1 this is the pi. Okay, for but a2 it will be 1 minus sine square theta, so that will be cos square theta. Okay, so this is our situation. Okay, and so this is why both are correct, so it is both IA and B here answer. Another question from reinforced. Maybe we should take a 5 minutes break here, and then we proceed further. Okay. So coming back, so this is the problem that we have. So the update and reinforce is given by this. Okay, so are they equal or not, these two? Okay, so as you can see that expectation can be carried over these two terms. Okay, so expectation of RT and you understand, right? Means like uh, expectation over x1 plus x2 plus x3 is like expectation of x1 plus expectation of x2 plus expectation of x3. So so this is like this term plus something is this. Okay, so what is that something? It is minus expectation of b. So b will come out. Okay, or you can write it as well inside and del ln pi a I theta t and divided by del theta t. Okay, so just writing it down. Okay, now what we have is, so if you take derivative of a log of something, so what we get is, so 1 by pi we will get, and another is that del by del theta t pi. Okay, so this is what we are going to get. Okay, now the expectation is with pi at. Okay, a theta t. So you can write this one as in place of expectation you can write a summation over a, means the previous form we are getting to, and this is like 1 by pi and del pi del by del theta t, and this is pi. Okay, and multiplied by pi. Okay, this is del t. So this pi cancels out, right? Pi pi, and now you have this one. Okay, 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 and now okay, so what you get is that summation of over a b del pi by del t del or del t del theta t. Okay, now one important thing to understand here is that, so we are summing over every action here. Okay, so summing over every actions of a probability is 1. Okay, but we are taking derivative with respect to that, with respect to theta t, another parameter. So derivative of 1 is 0. Okay, this is 0. Okay, so means these two do not have any difference, so this is the first option is the correct one, equal. Any doubt here? Any doubt?
No, sir.
Okay, so let's continue. Uh, so this is a policy search algorithm for multi-armed bandits problem, and so these conditions are there which following is true for the algorithm. Okay, so this is the question we have here, and so so which type of algorithm is that? Okay, first of all, so let's see. So first you can what you can do is that okay, first you should see that okay. Uh, so RT, there is dependence over RT. Okay. Is there any dependence? No. No, nothing on RT. That 1 is the indicator function. It is 1 if A equals to 80. Okay, otherwise 0. Okay. So if say it is A equals to 80. Okay. So what we get here is that so pi t plus 1 A, and this is equals to, so this is A is 80 and this is pi t A t and 1 minus alpha. Now this alpha times this is 1 in this case, so this will be RT plus 1 minus this is 1 in this case. Okay, this is 0. This is what we get. Okay, in case of 80. Okay, okay, so in case of 80 this is what we get. Okay, so for let's say pi t plus 1 in which it is not 80, so 80 a dash, say a dash is there. So what we get here is that this is pi t a dash, okay, and this is 1 minus alpha plus alpha times this becomes 0 and this becomes 0, so this is 1 minus r, alpha 1 minus r. Okay, so this is your thing. Okay, now what we can see here is that so the major thing is that what does we have here that it's like for a multi-armed bandit system. Okay, so there is like several A's possible. Okay, so you can understand that for every value of A, maybe 80 minus 1 or something like that. Okay, you will always get the same equation for the specific arm in question, and for anything other than that, you'll get this equation. Okay, so the alpha, the parameter alpha beta is there. Okay, so all the parameters actually equal, alpha equals to beta equals to gamma. Okay, like that. Okay, so it is actually a LRP problem. Okay, which is not in the option. Okay, and according to which that best arm has probability of 0.9. Okay, so the thing is that it would work well, and it's like in which the R and P enclose. Okay, so this is the answer actually. So according to the LRP system, it would work well if the base probability had arm is 0.9, resulting in this. So next best arm is 0.5. Okay, so 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 quite close. Okay, and high probability. Okay, so this is the answer. Okay, and moving to the next problem. So contextual bandit can be modeled as a full reinforcement learning problem. Yes, but like uh, only if the future states does not depend on the previous states. Okay, we can define an MDP with n states and the number of actions from each state correspond arm, and each bandit which every action is termination of the episode and given a reward according to corresponding. So each every action leads to termination of the episode, means that it does not give impact in the future. So that's it. Okay, so these two both are correct. Okay, so answer is A. Now what is true for an MDP? So Markovian property has to be fulfilled. So this is the one actually. Okay, which fulfills the Markovian property. Other than that, what we have here is that uh, other than that, none of them are Markovian property. Markovian property, you understand, like so our t plus 1 you are looking at, it only depends on the immediate previous one, that is st and at. Others are not important, okay, so only this is required. So 9 is done, and now 10. So we are taking a gamma greater than 1. Okay, here uh, so so if gamma is greater than 1, then the actual algorithm will not converge. Okay, uh, so it will always remember that the delayed rewards are better. Okay, because like as you go higher, t plus n, gamma becomes more. Okay, so that is more beneficial, so it takes importance of the delayed rewards more. Okay, so but it will not be able to learn properly, that is, it will not converge. Okay, because because you can understand that if it becomes lower and lower, then only it can converge, right? Convergence of sequence. Okay, so that part is there. Okay, and get to the our previous problem that we had here. This is the one, right? Okay, so what we have to do is that so as you can see, these are complementary of each other. If we add that complements to 1, okay, so we can use only one of these, क्योंकि means like for like it is for action A1. Okay, so only this one is important, A2 is not important. इसमें फंस गया था. Only A1, this one is only important. Okay, and now so it's not easily visible, so let's remove that one. And so what we need to do here is that so this w1 w2 is there, alpha rn is there, and now we need to take derivative of this pi logarithm of that, right? Where it was, here it is. Okay, uh, so So logarithm of that, okay. So let's take the logarithm of this, okay. So ln, so of course divide will become subtraction, okay, and this will become ln w1 transpose s minus ln e to the power w1 transpose s plus e to the power w2 transpose s. Okay, this is what we get. Now taking derivative with respect to w1, so what will this become? This will become s, okay, and this will become, so with respect to w1 we are looking at ln, so this will invert, okay, so this will come in the base, and then we're taking derivative of this one, and derivative will um, sum of derivatives, okay. So e to the power something, no change there, okay, w1 transpose s, and this will produce another s, so this is our answer. So I think this is the answer we are getting here. Next what we're getting is with this will w2, so it will be symmetric actually, so this is the answer as well. This is 1 and 3 answer, so answer is this one, okay. This is how you do it. Okay, so all the questions are done. Any doubt in this? Any doubt? Any doubt?
No, sir.
All clear? Okay, so we're moving a little slower, but like we'll catch up soon. This coming 2 weeks we'll increase the speed, okay, and we'll be able to catch up, okay, with the flow of the weeks that we are having. Okay, so thank you very much everyone. See you next week. Okay, have a nice day, enjoy the cricket match. Okay, bye.
Thank you, sir.